Hi everyone, this is Mr. West. Today we're doing a Kuta worksheet tutorial on linear programming. This is an extension of systems of inequalities. You'll see this in Algebra 2 advanced topics classes, and it's actually pretty relevant. It's kind of a cool topic, but it's pretty involved. So I'm going to try to break this down into the simplest way possible. It gives some instructions here. It's like a paragraph. I'll just kind of highlight that we have to start by graphing the constraints. Those are the linear inequalities, shading, and then this is the most important part when it comes to linear programming is testing the vertices, okay? That's kind of like the final step. That's the most important. I'm going to read through this problem just so you get an idea of what we're looking for with all the different constraints, etc. You need to buy some filing cabinets. So this is like a business. You know that cabinet X costs $10 per unit. Okay, I'm going to highlight that. Requires 6 square feet of floor space and holds 8 cubic feet of files. Okay. Cabinet Y, I'm going to change the color here. Orange. $20 per unit, requires 8 square feet of floor space and holds 12 cubic feet of files. You have been given $140 for this purchase, though you don't have to spend that much, meaning you can spend $120, $110, $139, etc. The office has room for no more than 72, I'm just going to leave that green, 72 square feet of cabinets. How many of which model should you buy in order to maximize storage volume? Okay, a couple things. You'll notice that I specifically chose blue. Where do these equations come from? So if you wanted to come up with the constraints yourselves, you could do that. But I'm glad they just give you the equation. So here we have 10x. That's where this comes from. That's $10 per unit. And then this is $20 per unit. And it has to be less than $140. That's one of the constraints. So the amount of money that you spend on cabinet X and cabinet Y needs to be less than $140. So if it's $10 per cabinet, then you just multiply 10 times the number of cabinets. That's where this comes from, okay? The next thing is the amount of square feet it takes up. So here we have 72 square feet is the maximum, and it's got to be less than that. So it takes up 6 square feet for X, and it takes up 8 square feet for Y, okay? So then there's that equation. Our inequality, it's not an equation actually. And then our objective function, okay? This is the most important part. This is the thing we're trying to maximize, okay? We want to maximize this because we want to get the best bang for our buck. We want the most amount of file cabinet storage with the least amount of space stored with spending the least amount of money. So there's a lot going on here. So this is a very relevant problem. Companies do stuff like this all the time. Okay, so we get, 8 cubic feet for cabinet X, and then cabinet Y is a little bit bigger. It takes up 12 cubic feet, okay? It doesn't take up, it offers that much storage. So this is our objective function. We're going to be working on that on the last thing, just for simplicity's sake. Okay, so the first thing is we're going to be graphing the constraints. So here's the constraints. We need to graph these. I recommend getting these into slope-intercept form first. That means we need to solve for Y. So we have here, I'm just going to rewrite it, 10x plus 20y, less than or equal to 140. First thing I'm going to do is I'm going to subtract 10x because I'm trying to get the y alone. 20y less than or equal to 140 minus 10x. Now what I need to do is I need to divide by 20, and I'm dividing everything by 20. Okay, so I have y is less than or equal to 140 divided by 20, that's 7 minus 1/2 x. I know you're like, oh my gosh, not a fraction. It's not that bad, okay? It's not that bad because, oh, we're going to make this one purple, by the way. It's not that bad because that's our rise over the run, and this is our, the 7 is our y-intercept. Rise over run, negative 1/2, y-intercept, okay? So it's going to start with 7, that's our y-intercept. Okay, and I'm going to go down 1, that was my rise, and then over 2. Okay, just as a quick reminder. And then I can connect my dots. And if you have a straight line maker like this is Notability. Awesome program, by the way. And we draw it, and I think it's going through all of them pretty perfectly. Okay, it should be going just about, my first starting position wasn't great. Okay, I don't know if I did a great job, actually. No, I didn't. Let me redo it. Okay, sometimes you win, sometimes you lose. So it's got to end up on 14. Okay, and there's a reason why I'm trying to graph this pretty precisely. Okay, let's do the next color. Let's use this pink color. Okay. Oh, I forgot to shade. So we also need to shade as it describes in the instructions, original instructions. and its y is less than, okay, so that means I need to shade below the line. Anytime its y is less than, it's shade below the line. And you can check out some other videos I have on graphing linear systems of inequalities, and you can see that I break down if its y is less than, you shade below. If its y is greater than, with everything else on the right side, then it's shade above, okay? And it's also going to be a solid line like we drew instead of a dotted line, because it's not just less than, it's less than or equal to. That's why it's a solid line. Okay, so that was our first one. Now we're going to graph our second one. And again, what I want to do is I want to get the y alone. So I'm subtracting 6x from both sides. 8y less than or equal to, we'll just do 72 minus 6x, and divide by 8 to everything. Okay, so we get y is less than or equal to 9 minus, I'm going to reduce this fraction, 3 over 4x. Okay, so my y-intercept is 9. And now this time I'm going down 3, 1, 2, 3, over 4, 1, 2, 3, 4. Okay, and I'm going to repeat that process, and I'm just going to do it 1, 2, 3, 1, 2, 3, 4. Okay, 1, 2, 3, 1, 2, 3, 4. Okay, so this is where I end up. I'm going to connect my dots, and boom. Now, this one also is shade below. It's a solid line because we have less than or equal to, and it's below because it's less than. So I'm going to shade this also. I'm going to make it a little bit bigger just so we can not waste so much time watching me shade. Okay, this isn't an art channel, although I would like to do art sometime on it. Bob Ross video maybe? Who knows? Okay, maybe once I reach 1,000 subscribers, I'll do that. Getting close. Okay, so anyway, I finished graphing it, and you can clearly see we have a solution set here. Okay, the solution set, also known for these types of linear programming problems, is called the feasible region. Okay, so this is where all these constraints are satisfied. Okay, so this is the feasible region. This is where we need to look. Obviously, we wouldn't look here because that's not within the confines. We'd be having file cabinets fall out of the room because there's too many. Okay, so we need to live in this area, and specifically, we need to look for these points. We want to look at the extremes, okay, because we're trying to maximize stuff. Obviously, we could have only one of each file cabinet, but we wouldn't be maximizing the amount of file storage we have, okay? We want to maximize the amount of storage for everything, so that's why we go to the maxes, the extremes, here, here, and here. And what are those points? We need to know what the x and y values of those points are. Well, I should probably rewind a little bit. What does this x-axis represent? That represents the number of cabinet X. So these are our cabinet X. So each one of these, okay, right here, for example, that value of 12, that means 12 cabinets of cabinet X. And likewise, this is cabinet Y. Okay, so each one of these is another cabinet. So in this case, back to this example, ugly circle there, sorry, cabinet Y. Okay, we have 0 of cabinet Y. So this would be a way we can maximize this, 12 of X and 0 of Y. Likewise, we have this one, 0 X cabinets and 7 Y cabinets is one of the ways we can maximize our objective function. Okay, remember, maximize space with the best bang for our buck. And then we have this one, 8 and 3. Okay, so how do we know which one is the best solution? Okay, what we need to do is we need to test each one of these in the objective function. So let me show you what that looks like. Here we have V, and I'm probably going to reuse the same one. And we need to rewrite everything, 8, but I'm not writing X, I'm going to write parentheses, okay? And then we have, I'm just going to use yellow, plus, and then we have our Y, which is, I used orange, right? 12, and then parentheses. What am I doing here is I'm putting in these different combos. Okay, so the first combo I'm going to do is I'm going to do 0, 7. So I'm going to plug in 0 for X, and I'll plug in 7 for Y and see what I get. When I do that, I get 0 plus 84. So I get, that's 84, right? Yeah, 12 times 7, 84, yeah. So I'm going to get 84, okay? The units, that's square footage, I believe, okay? How much space, how much filing storage I have. Cubic yards, I think. So cubic feet of storage. So I got 84 cubic feet of storage by getting 0 of cabinet X and just getting 7 cabinet Ys, okay? So that's one way we can do that, okay? I'm gonna just minimize this and move it to the side so you can see that this was our first option, okay, over here. Now, let's try another combo. The other combo was 8 and 3. So we're gonna plug in 8 of cabinet X and 3 of cabinet Y. What happens when I do that? I get 64 plus 36. Well, that gives me 100 cubic feet. Okay, so already the 8 and 3 combo is winning. We don't even have to consider this one anymore. Okay, that one's garbage. Let me actually exit out so you know that we're not choosing it because it's not enough storage. And then we have our final option. Okay, so I'm leaving this one off to the side. Final option was 12 of cabinet X and 0 of Y. So I'm going to plug in 12 guys here, and I'm plugging 0 for Y. So 12 times 8, or what color am I using? Just use green. 12 times 8, 96 plus 0. So this one's 96 cubic feet. So we know that we have a winner, and that is the 8 and 3 combination right here. That is our maximum. That maximizes our objective function. So we want 8 X cabinets, and we want 3 Y cabinets. And that will maximize our cubic feet of storage for this particular office. So that's all there is for linear programming. This is a tough concept. Let me know if you want more of this. It's kind of a cool and relevant topic in terms of business. Businesses do stuff like this all the time. Programming, computer programming, stuff like this happens all the time. But anyway, thanks for stopping by. I look forward to seeing you next time right here on West Explains Best.